So, like a lot of our other lectures, I want to start with some news. So this was over the summer. This article came up on the front page, not the front page of Wall Street Journal, but the front page of their technology section, and it says that flash memory have suddenly become hot, especially for application into the storage space, cloud computing, and it says flash memory is celebrating its 25th year since its invention this year. So we'll talk later. I'll try to give you some perspective why this is the case, why this is happening, and this is another thing which was later part of last year, actually more than a year ago, and it says this is the latest flash memory chip you can buy, the most advanced one. It says it's a 64 gigabit die, or if you convert it into byte, it's a 8 gigabyte die. The difference between bit and byte is bit is usually a small b, byte is a capital B. So keep those in mind when you read news articles like that. It also says that it's a 2-bit per cell, or it says X2, and you'll see this term again, X2, X3, X4. So we'll talk about what that means. And another thing is that it says 19 nanometer, but we'll see later that it's not exactly 19 nanometer by 19 nanometer. It's actually one of these two, either the bit line or the word line. One of them is more closer to each other rather than the other. So earlier in the first lecture, I asked you to name semiconductor companies in the Bay Area. None of you, actually, I was very disappointed that none of you named any of these companies. These are all flash memory companies, mostly located in the Bay Area. In fact, this is a very hot segment of the market now. Last year itself, $400 million of venture capital were invested in these companies. Actually, the correct number is 389 million, but that doesn't sound as good. But so the thing we want to answer is, what do they do, and why is there so much venture capital action in this space? So these are common applications of flash memory. You must have seen USB back in the 2004, iPod Nano, iPhone, MacBook Air, more recently iPad and tablets. And what has resulted because of that is that this market, which is NAND flash, so there are two kinds of flash, the NOR flash, which is in white, and the NAND flash, which is in blue. So that has really exploded in this post-PC era. In 2010, it was close to a $20 billion market. And the question now is that, is it going to saturate, or is it going to actually saturate, or is it going to continue growing? So think about it, you already have all these tablets and smartphones, but so they put out different models, right? 8 gig, 16 gig, 32 gig. Most of the people actually, more than 70% of the people buy the lowest capacity one, and they're preferring to store their data over the cloud. Apple has a solution, right? Dropbox, Box, Google Drive, and all these companies are not, they're still hard disk based, the companies which store in the cloud. So the question is it going to saturate, or is it going to continue growing? And the good answer is a lot of cloud storage is also moving to flash memory. So you might have, I'm sure all of you use, some of you might use Chrome, but all of you might have used Google search, and this product, right, where you start typing and it gives you the relevant result. And it's all enabled by storing the whole internet on a NAND flash memory. And Google, in fact, is one of the largest buyers of enterprise kind of flash storage disk. And there's a huge advantage you get in terms of power if you move from hard disk drive to a flash, and that's actually more of a driving factor than the speed, because as we'll see later, storing or writing into flash is much more energy efficient as compared to writing on a flash disk drive. So with that introduction, what I want to do first is to cover some basics of flash memory. So I want to cover 4 things. The two different architecture, NAND and NOR. I want to cover how do you program a flash memory cell, how do you erase it, then how long you can store it, which is also called as retention, how many times you can read and write to it, which is called endurance or also called cycling. And then the last thing is this multi-level flash, that is having one cell but storing multiple bits into it. So there are essentially 2 different architectures that you can have for flash. One is NAND and the other is NOR. The difference is that in a NOR architecture you have your bit line, which is this black contact over here connecting to each of your cells. So you can, if you look at the stick diagram over here, you can essentially, if you look at the circuit diagram here, you can individually address each of the cells. So you can select a particular cell, selecting this bit line, and then you can select the word line and you can address each of the cells. Compared to NAND, essentially you get rid of all these black contacts. So you have all these cells connected in series. And the only way you can address one cell is that if you address all of the rest of the others. So if you want to read this cell, you first have to turn on all these other cells. But the advantage is that, as you can see, this is much more compact as compared to this one. So this has a feature size of close to 4F square, between 4 and 5F square. This one has a feature size of 10F square. Even though these 2 cells share one bit line contact, so you drop 1 for 2, but since the design rules for dropping a contact are more relaxed, since it's dropping from a different layer, you essentially get twice the area as compared to this one. So you get a feature size of 10F square. So the cell size I just described, NAND you get 5F square, NOR you get 10F square. Similarly, if you want to read a cell over here, you can very quickly read it. You can read it in a matter of tens of nanoseconds. DRAM memory, if you know, it has a similar read latency. NAND flash, if you want to read one cell, you need to turn all of them, and then only you can access this bit. So it has a read time of a few microseconds. So it's, as you can see, it's much slower to read. But the best analogy I've seen is that this is like living in a own house, so you can get out on the road as you want. This is like living in a apartment building, multi-story apartment building. Whenever you want to get out, you have to walk through all the other floors. You have to disturb all the people around you, but that's a good analogy to understand it.
Question.
Yes.
Can you talk about the cell size?
Yes.
What's the definition of 1F squared?
So F is the minimum feature size you can print. So suppose you can print a feature size of F. You have to separate them by the features by a feature size of F2. So you get like 2F, and similarly 2F in this direction, so 4F square. So the reason why it's called NOR or NAND is because the circuit diagram at least has some resemblance to how NAND and NOR gates look. So if you remember NOR gates from your basic electronic class, it has essentially, if you need to perform any operation, all these signal has to pass through both A and B. As compared to NOR, each of them has an individual contact to the ground. So that's why it's called NAND and NOR, even though it's a memory device, because it looks similar to this circuit diagram. So as I described, that since you don't have this bit line contact between 2 adjacent cells, you can pack that whole cell. So in this case, let's see, I have 8 cells, and if I draw them in a NAND fashion, I'm consuming this much length, 59 micron. But if I just connect them in a NAND fashion, I'm consuming half the length, or 25 microns. So even though there are disadvantages of living in an apartment building, you can get significant cost advantages. And this is a more realistic picture of an actual cross-section of cells connected. And here you can see there's in a NOR flash, you need to drop this contact between each of these two cells. You have to drop these contacts. As compared to a NAND, it looks very clean. There are no contacts. The only contact you have is towards the beginning and towards the end of a string. So you get half the area as compared to 10f square, you get 5f square. And you get half the price as well, since half the area and it's you can pack twice the cells, so it's half the price. And that's why this market has, NAND has grown much more faster as compared to NOR. Sometimes it has tried to displace both NOR and DRAM, because essentially it's so cheap, because you can fabricate it so compactly. So I want to come to how this works. So to understand how it works, we can borrow this equation from our 216 or a similar device class, where you might have studied the threshold voltage, and it depends upon these normal terms, but it also has these terms. There's some charge trapped in your MOS capacitor. So if there's some charge trapped in your MOS capacitor at a distance of dt from your top gate, your threshold voltage shifts by this amount. That is, Q is the amount of charge trapped into your distance divided by the dielectric constant of your insulator. And you can rearrange this term. That is, you can divide this epsilon by dt, and that will give you that capacitance term. So what happens is that if you don't have any charge, you have threshold voltages here. If you have some charge trapped in there, you get a different threshold voltage. So the flash memory is essentially nothing but it's a more convenient way of trapping charge in your gate stack. So this is how it looks like. So you have a source and drain, similar to what you'll have on a normal transistor, but you have this extra thing called as a floating gate, and it's floating because there's no terminal available to it. You can see there are 3 terminals sticking here, source, drain, and gate, but there's no terminal connecting the floating gate. And it's separated from this channel by this oxide, which is called as tunnel oxide. And it's called tunnel oxide because most of your tunneling of electrons and holes, it occurs from the channel into this floating gate through this oxide. So that's why it's called tunnel oxide. This one is called IPD, or interpoly dielectric. And traditionally these two poly gate, this floating gate and the control gate, were made out of polysilicon. So it was separating two poly material. That's why it was called interpoly dielectric. So again, what happens is if you don't have any charge, you get one threshold voltage. And if you store charge, you get another threshold voltage. So that's how this device works. And so depending upon whether if you have charge, no charge stored over here, your electrons can easily flow from your source to your drain, as compared to if you have charge present in your control gate, it prevents that electrons from flowing, because these electrons will try to repel the electron in the channel, and you have to apply an extra gate voltage to allow that flow of the current. So what you do is essentially how you read the cell is you apply a certain voltage which is in between these two states. So depending upon whether there is charge or not, if there was no charge, you'll get a high current, and if there was charge present, you'll get no current. And To program and erase the cell, which I'll just describe to you, you either apply a high positive voltage on your control gate, or you apply a high negative voltage on your control gate. So in reality, you don't get one threshold voltage, you get a distribution of them. So you'll get a distribution of voltages in your erase state, and you'll get a distribution of voltages in your program state. When you want to write the cell, you tunnel your electrons from your channel into your floating gate. When you want to erase it, you tunnel them out from the floating gate into the channel. And this is again, as I just explained, if you want to read them, you apply this particular voltage on the cell you want to read. But the problem is, or not the problem, but the limiter to your reading speed is you need to turn all of these other cells, all of your neighbors above and below to get to the cell or get to the apartment you want to reach. So what you do is on those other cells, you apply a voltage which is high enough such that you definitely turn them on. So on those other cells you apply, which is called the pass gate voltage, to essentially allow them to pass or allow them to conduct. And this is what limits the speed at which you can read that particular cell. It also causes a lot of disturbs because there are unintentional consequences of applying this voltage. You might softly program a cell, or you might disturb a cell adjacent to it. So this is one of the limitations of a NAND flash or a NAND architecture for a memory. So I want to go through this rather quickly, but this is a snapshot from one of the videos. So to understand this, how this the voltage in your floating gate is related to the rest of the electrodes, you can write this simple Q equal to CV relationship, and you can relate your floating gate voltage to all the capacitances. And what you can do is then rearrange these terms such that you write them in terms of your floating gate voltage. So I want to just spend 1 minute to explain what this final relationship is. So this final relationship is what is relating your floating gate voltage. And there are two main things you want to relate it to: what voltage you apply on the control gate, and how much charge is stored in the floating gate. And you can see in this relationship, this floating gate voltage is related to your control gate voltage by this thing I'm calling as gate coupling ratio, which is the ratio of my capacitance with the control gate divided by the total capacitance of the cell. And a general industrial practice is you want to keep this at least above 0.6 for this cell to work properly. In general, you want to keep it as high as possible, because you want, as soon as you apply something on the control gate, you want your cell to get programmed fast, or you want to transfer that voltage to your floating gate. But usually what you achieve in practice is close to 0.6. And then it's related to this charge on the floating gate simply by the charge divided by the total capacitance, or the self-capacitance. So this is an important relationship to keep in mind to understand how the cell will work. So essentially, if you apply a high voltage on your control gate, suppose say you apply 10 volts on your control gate, it will transform to say 0.6, it's not 0.6, 6 or 7 volt on your floating gate. Similarly, if you apply minus 10, it will correspond to minus 6 or 7 on your floating gate. Another thing to understand, needed to understand the flash memory is essentially is the tunneling phenomena. And again, you might have covered this already in your device course, but just to revise you have different regimes of tunneling. One is first of all, if you don't have any potential difference between your two electrodes, there's no tunneling across that dielectric. If you have a very high potential difference, you see a triangular barrier for these carriers to tunnel from here to here, and that's called Fowler-Nordheim or FN tunneling regime. And the other one is if your voltage is somewhere in between. It's higher than 0, but it's not as high as Fowler NORDIM. So your electrons see this trapezoidal barrier for tunneling, and it's called a direct tunneling. And if you plot your gate current in a capacitor as a function, in a MOS kind of structure as a function of your gate voltage, you can clearly identify these three regimes. So you'll have a very low current, that is essentially no tunneling regime. Then you'll have a very large dependence on your gate voltage, that's typically your direct tunneling regime. And then you have a very high current but a weaker gate voltage dependence, that is your Fowler NORDIM tunneling regime. So when you program a cell, you typically apply a very high voltage and you operate in a Fowler NORDIM tunneling regime. When you want to retain that charge, you want essentially low potential difference, and you want to be in this regime where there's no tunneling happening.